we are going Facebook Live.
Okay, that sounds good. Let's see. We have few people here. Okay, let me share my screen.
Just a minute. Just a minute. I have to first share my own screen to some. There is one small promotional video. Then I will allow you. Okay.
Okay. Okay. Sure. Thanks.
Thank you. Okay, I am sharing my screen. There is a small promotional video. So, hello, is it audible?
Yes, I can hear you.
Yeah. So, just dear attendees and panelists, today we have Aniruddha Maiti. He is currently final year doctoral student. He is doing his final year doctoral studies at Department of Computers and Information Science, Temple University, Philadelphia. His research interests are in the domains of natural language processing, machine learning, hypothesis testing, and spatial epidemiology. He is also a data scientist working on healthcare and social media analytics at HVH Precision Analytics. As a data scientist, he is doing research and development on the methodologies for predictive analysis with social media data and electronic health records. So I am warmly welcoming Aniruddha, and he is like one of my friends from a long time. So Aniruddha,
Hi, thank you, Dr. Adab, for nice introduction.
yeah.
Should I
So yeah,
share
you may
my
share your
screen?
screen.
Okay, let's see. Preview. Okay.
Yeah,
Is
it
it
is visible. Yeah,
visible?
it is visible. Yeah, it is visible. So now control is yours. Thank you.
Now, let me uh, let me start again by thanking Dr. Adab for arranging this talk. I'm glad to present some of the works that I have been doing during my PhD. As Dr. Adab mentioned, I am a final year PhD student, and I am also working in the domain of healthcare analytics for more than a year now. So today's talk is about a prediction task. It's about how to predict spatially high-risk regions from long-term residential history of patients. Now, let me jump into the problem statement. I'll go through the talk by using simple examples, which are easy to follow, and hopefully, our participants would get the basics of this problem and the challenges that involves. Now, the problem definition is how to find high-risk geographic regions. That means that we are given a study area and we have to tell whether a region is high risk or not. Now, what do I mean by high risk? I mean that if a person lives in that region, he is more likely to get a disease. So that's the definition of high risk. Why are we interested to know this thing? We are interested because actually there are some diseases that are caused by harmful environmental exposures. For example, presence of some hazardous elements in the environment. And if we somehow find high risk regions, then we can establish some causality. For example, let's say there is a chemical factory, then we might say, okay, there are some chemicals there that are causing that disease. Maybe there is a particular source of water which is contaminated, and then we can establish that link. So that's the idea. That's why we are interested to know, interested to find out high risk regions. Now, given this problem, if we think about it, the solution might look straightforward. Well, why don't we plot all the people and just look for clusters with high density? For example, I have shown here a fixed JISIASR map, and there are people who have been diagnosed with that disease. And of course, there are few clusters as you can see there. Now the question is, what can go wrong if we do like this? Now, if we think about it, it might so happen that those places are having high number of cases because those are population centers. That means those are big cities and lot of population density. And we are observing high number of cases, not because those places have high risk, but because a lot of people live there, and so the number of people with that disease is high. So here is this thing. So blue dots, these are normal people who don't have the disease, and the red ones are the people who have been diagnosed with the disease. Now, as you can see that if we just go by the red points, then we will come to an erroneous conclusion, because the places what we thought previously as clusters are just big population centers, big cities and all. Now, so we found out that our previous assumption, like previous approach, did not work. Now, what to do in this case? Well, why don't we just consider the population as well? And instead of just looking into cases, that means the red dots, why don't we look into the ratios? And essentially, that approach is what a lot of people apply in this type of studies. What they do, they essentially calculate the ratio or the proportion of cases as compared to the population, and they try to look for places with having that ratio is high. That means the proportion is high. Now, from here, let us think about how we drew these points on the map. So I said that those are people, but people are not stationary points. They move about, and they don't stay in one place. So basically what I did, I plotted residences at the time of diagnosis. Why? Because people tend to spend a lot of time at home, and we can use the residences of people, that is where they live, their home, as a proxy to environmental exposures. Because if their home is in a place where there is environmental hazards, more likely the person is exposed to that hazard, right? So I hope so far it's good. It's pretty simple actually. So now given this, that's why a lot of people use residences at the time of diagnosis as a proxy, and they use that as a location point, XY coordinate. And what they do, they perform studies in case control setting. I'll come to that. What is that case control setting? And then they basically what they do is they look for clusters. There are methods, advanced statistical techniques to do that. We can also employ standard clustering schemes as well. Now, what can go wrong in this approach? Clearly, the use of residences as a proxy to environmental exposures is good because people tend to spend a lot of time at their home. But what if people change residence? Let's say this example where I have shown a potential cluster. There are very few normal people, normal in the sense that they don't have the disease, and there are two cases. And I say, okay, let's say this is a cluster, high risk region. But what is the guarantee that those two people lived there long enough to get exposed? What if those two people just moved in and got diagnosed? it happens, people change residences. And actually those diseases that I am talking about, they don't develop overnight. There is one latency period where a person has to be exposed throughout a long period of time to develop that disease gradually. So in this type of scenario, what approach we can take? Let us think about that one. So if we know the latency period, let's say a disease takes 10 years of time to develop, then we can go back in history, see where people had lived 10 years ago, and do essentially the same thing to find high risk cluster. So it is basically a retrospective analysis where we can, in this figure, the above figure, we see that those two people used to live somewhere else, the blue ones, and then they moved to the new place. And so if we do this retrospective analysis 10 years back, we will say, okay, not the above one, but the below the blue circle is actually the high risk area, because 10 years ago people used to live there. But that approach, while it is good, and there are studies that employ this type of analysis, there are a couple of drawbacks. First of all, knowing the latency period of disease is not a straightforward task. For a lot of diseases, it is not a fixed time. It's not that, okay, 10 years ago, if you got exposed, 10 years later, you will develop the disease. It's not like that. It's a gradual process and things like that. And there is also another problem, which is people's movement pattern are not that simple. Let's say 10 years ago, they used to live there. Consider the below geometry. So they used to live 10 years ago somewhere, but then after 1 year, they moved to someplace else, spent there 9 years, and now they are living in their current position, which is now. Now, if we do 10 years retrospective analysis, then we will essentially see that there is a cluster which is denoted by the blue circle in the above map. But those two people, they actually did not live there much. They moved again to someplace else, spent there most of their time, and then they are currently moving in their current position. So actually what we should have done, we should have considered somehow the place where they spend most of their time as a potential candidate, not the place where they are living now, not the place where they were living 10 years ago. So this study is, like today's talk, is basically related to this type of approaches, like how to take care, how to take into consideration all the places where people had lived, and then do some kind of analysis to find high risk spatial regions. So of course, as I said, so we are considering long-term residential history, not present, not 10 years back. It is considering all the places that people lived. And then we have to come up with some sort of weighting scheme so that we can give more weight to places where people have spent more time. For example, let us see this example where in one place, those two people live for 1 year. There is another place where they live for 2 years, and there is one place where they live for 7 years. Of course, we can give simple weight and normalize, and so the weight will become 0.1, 0.2, and 0.7. So basically, this is the scheme, entire scheme. Of course, I am simplifying things, but the idea is like this. Now the question, why didn't people do this so far? There are a couple of obstacles. First of all, the data availability. Accessing long-term residential history data is not easy task. One way to gather such data is by interviewing people, like survey, but that process is expensive. For example, let's say there is 20,000 people, and if we have to go to each of the person and ask for their past residential histories for past 20 years, that is very expensive, and people also forget where they used to live 10 years back. Those problems are there. On the other hand, residences at the time of diagnosis, like their current address when they got diagnosed, is easily available, because those information is like this information is collected as a routine information collection procedure while a person interacts with healthcare facility. Because if you sign up for a doctor's appointment, probably you have to give those kind of information, what is your current address, for ease of communication, and all these things. But good news is that today there are some commercial vendors that collect residential history data. They don't collect it, they actually compile it. They compile it from lot of sources, different sources: credit data, driving license, litigation data, business related data. Those data sources they first accumulate, then they try to identify the person involved, and then they try to build a continuous residential timeline corresponding to a person. And also there are some countries, for example, there are some Nordic countries that maintain a population registry, and those population registry data is available to researchers. So there are some sources, at least now, which can be used to solve this problem. Now let me talk about the framework. Okay, one thing I would request, if there is any confusion, I would always encourage any interruption. Please don't hesitate to interrupt me. So the framework that in today's talk. So step one. First step is to divide the entire region into sub-regions. Why? Because there are a lot of people, and we cannot just use every people's address and put one point there. It is much easier if we aggregate them at a higher level. So first we divide the entire geography into some convenient sub-regions. For example, in the study that I am talking about, we used census tracts, which is some administrative division, to divide our study area. Now the next one is that the example that I had shown, where people used to live 7 years, 2 years, and 1 year in 3 different places. It's basically constructing a vector which contains all those information. So we have to create a vector representation of study subjects. Study subject means the people that we are talking about. And how to do that? From residential history data. So that's our vector representation of the study subjects. And also we have to know which people have disease and which people don't have the disease. So that's another variable, which is case control status, denoted by Y, and our input would be X, output would be Y. So the idea is to model it in such a way that if we give this input vector we say that, okay, this person lived here, 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 and here, then we would be able to say what is the probability of that person having the disease that we are concerned with. I'll explain this. So again, so our input is X, which is of length M. M is the number of subregions. I'll explain. So let's say this figure, there are 20 subregions, and there is one person who lived in 4 places, inside 4 subregions. He lived in subregion 1 for some time, then in subregion 2 for majority of his time, and subregion 8 and 12. And let's say we give weight. So X1, the first component of the representation, have some number, some fraction of time the person spent inside subregion 1. The second number, 0.5, is the how much time the person spent inside subregion 2, and then all other are 0 except for 8 and 12. So I hope it is straightforward. So these numbers, these fractions are nothing but how much time, how much fraction of the time the person spent inside the corresponding subregion. So the length of X is 20 because there are 20 such subregions. And this is the representation of only one person. If we have, let's say, 10,000 persons, then we have 10,000 such vectors of length 20. So that is our input. And our model is to somehow use this input inside a function so that we can predict, not predict, like we can tell the probability of the person having that disease. And inside the model, do some trick so that we can also identify high risk spatial regions as well. So the idea is pretty simple. Our model is f of x, where x is the input and y is the sort of the probability, how much the likely the person has the disease. And we used simple logistic model because logistic model is good for probability because output is in between 0 and 1. And it is simple, also easy to interpret. That's why we used logistic function to model this type of things. Logistic is a sort of a function. So if we know x, if we know r, then we know the probability. I'll give some examples also. So that's basically the setting. So how to construct it? X, again, we apply simple weighting scheme. Most time people resides inside a subregion, we give more weight. Let's say we have 10,000 people and 20 subregions, then our input data is 10,000 times 20. Each person has a representation by vector x, which is of length 20, the number of subregions. And the parameter in the model are the risks, which is represented by r. That r is here in logistic function, which is actually saying how much risk that area, the subregion, has. I'll explain again. So let's see this example. Let's see the previous figure. So the person lived in first place, first subregion, 0.2 amount of time, fraction of time. Second is 0.5. In that way, we constructed a vector of length 20. So our x corresponding to the person is of length 20, and we have some numbers. And those numbers are derived from residential history of the person. Now, if we know r, somehow, let's say somebody informed us, okay, the risk here is 0.2, 0.3, like that. If we know r, then we can compute r transpose x, which is nothing but the multiplication of those numbers, 0.2 times the number R1. Let's say R1 is 1, 0.5, R2. These are just small numbers. And we can construct this R transpose X1. This output would be just, these are actually plus. So these number, if we sum them up, we will get this R transpose Xi. And this is just a single number. If we input that number inside logistic function, we'll get some number, some output in between 0 and 1, and we can interpret that output as a probability. But what is the problem? The problem here is that we really don't know what are the true risks of the subregions. So we really don't know R. So it is a kind of machine learning problem where R is the parameter. We have to come up with the optimal solution for R. How to do this? It's basically a sort of machine learning problem where we have input, we have output, we have some parameter of the model, and we have to define some cost function or loss function which we can optimize to get the optimal parameter R. So we can start with random R, random guesses, and calculate output of the logistic function. How many output we would have if we have 10,000 people? We have 10,000 such numbers. Those are basically probabilities. Let's say our output is 0.3 for seventh person. This is an example. Let's say seventh individual has got output 0.3 using the random guesses of R. Then from the data set, we also know that person has got the disease. That means his disease status is 1. Then we know, okay, our model had made some mistake. How much mistake? 1 minus 0.3. Now we can use any loss function. For example, we can use mean square and those things. Any difference between 1 and 0.3, we can square them, add them. And then we can update R based on this loss function using gradient descent or Newton-Raphson, those standard optimization schemes. Now the fun part, let's say we know that now our model can optimize, and we got to know what is the R. R means the risk of every subregion. And let's say I plotted the risks now. So the dark means high, let's say the light color means low. Now, if a place has high value of R, the risk, what does that mean? That means actually that a lot of people who have been diagnosed with the disease have spent majority of their time inside those subregions. That really means, because logistic function is kind of a accumulative function. So the more people will live there, the risk would be more. So this is the main trick, main idea of this work. But a lot of things can go wrong here as well. So we'll discuss those things. First, what can go wrong? First thing is the bias. Bias is a very popular term in this type of studies. Let's say people's movement pattern, demography are such that a subregion is showing high risk, not because of bad environment or anything, but simply because of the demography or the people's movement pattern. Example, let's say there is a subregion where a lot of old people live. And why would that be? Because let's say it is a seashore and a lot of people buy houses there after their retirement. Those type of special cases. For example, in the United States, if old people move to Florida, so Florida has a high proportion of aged people. Now the subregion which has a lot of those old people, they are showing a lot of cases, not because that environment is bad or there is some hazardous element involved, just simply because there are more number of old people, and old people are more likely to have the disease. So our model does not take care of these things. So we have to somehow come up with ideas to remove that kind of bias from the study. So solution, there are some straightforward solution to that, which are used extensively in spatial epidemiology or any type of epidemiology studies. They call it case control matching. What is that? We took one case, and corresponding to that case means the person with the disease, we try to find controls, that means people who don't have the disease, which matched exactly with respect to all other variables that might be available, that might affect our result. For example, in this case, age, I talked about age, also a person's sex, race or ethnicity, birth year, etc. Those all things might affect these type of studies. So we took one case and we try to find controls who are exactly same as that the case, except for the disease status, because control have disease status 0, cases have disease status 1. Now let's say we choose 5 controls corresponding to one case, and let's say we have 1,000 cases in total, so we would have 5,000 controls. So we have in our data set, we have 10,000 positives and 5,000 zeros. So that's our matched case control data set, and it is constructed in such a way that case and controls are not separable in the matched data. So we have total 6,000 data. Those are not separable in terms of demographic variables such as age, sex, etc., because we have created the data set in such a way. So that brings to our step 0. So before doing anything, we have to construct that type of matched case control data set in order to do any type of, in order to do this type of studies. So that's our step 0. First, create a matched case control data set, and then do all those modelings and finding out parameters, etc. Now let's say, so we learned how to model it, how to model the problem, how to come up with a solution and find risks. But people won't believe. If we say like, okay, this place has high risk, of course the question would be how much sure we are, like what is the confidence level. So we have to come up with some framework that can give us a confidence level on the predicted risks. So the solution is that we have to think the risks are some sort of test statistic, and we have to come up with a framework that can say how much likely a place, a sub-region is to have high risk. I'll explain. Okay, I would stop here for a moment, and I would like to ask if anybody has any question so far. Okay. Okay, so no question so far. Now the step 4, that is the final step. So now we know the risks are, let's say it's 2.3. To know how significant it is, the standard way that statisticians like employ is they try to draw the distribution of R and try to see where that value that we are seeing from the data set lies. For example, here it is kind of in the extreme end of the distribution, and it's likely it's a special case. It's not something that we we are likely to see if there is nothing going on. So we know about those tests, and there are lots of techniques of that. There are lots of standard measures. One of the measure is, let's say, 95% confidence interval, and there are assumptions. For example, if statistic is normally distributed, then there are some techniques to do this type of studies. But there is one little problem. Problem is, to understand that problem, we have to understand little bit in depth. So basically, how we drew this distribution of R? It is the distribution of the statistic under the null hypothesis. So in hypothesis testing, what people do, they create hypotheses which are contradicting. So one is null hypothesis, which is observed risk of a subregion is not an aberration. So it's kind of normally what we would see. And the alternate hypothesis is something that we are trying to prove or disprove, that risk is significantly higher. And to do this type of hypothesis testing, we have to know the distribution of R under the null hypothesis, so that we can see where the observed value of R, which is 2.3 in this case, lies in the extreme of the distribution or not. So basic idea is that like this. So we have one distribution and we have the true value of a statistic, and we try to see where that value lies, whether it is in the middle of the distribution, where that is like normal case, or whether it is in some extreme end. So to do this, as we don't know the distribution under the null hypothesis, what can be done here is randomized testing. People call it sometimes Monte Carlo hypothesis testing. So what people do, they shuffle the case control variables randomly, let's say 1,000 times or 100 times. So we had actually Y, that is the disease status, let's say 0, 1, 1, 0, 0. 0 means people don't have disease, 1 means the person has got the disease, and we shuffle these variables and create simulated data. We shuffle 1,000 times, let's say. And when you shuffle these things, we basically essentially are creating a null hypothesis. That means we don't know anything. People's movement pattern remains same. People demographic information remains same, but their case control statuses are just random because we have shuffled randomly. And we try to do the same experiment again on these simulated data to see what the risk related to, what is the risk related to a subregion. If we do this experiment 1,000 times, we would calculate the value of R 1,000 times again. Those values are on these simulated data, simulated under the null hypothesis, assuming without assuming anything, and we have 1,000 such R values. Now we can see where our original R lies. If it is too high compared to the 1,000 values that we have calculated, we can say, okay, that risk is really high. It is some sort of it is not normal. It is some sort of aberration. So that's the basic idea. So simulate 1,000 times under the null hypothesis and see where the risk lies. If it is within 5% of the top data, then we say, okay, it's a high risk, and we can assign p-value and all. So that's the that's the total framework. So I'll again repeat. First, case control matched data set. Then we have to model, and from the model we derive the optimal value of the parameter, which we are calling as statistic. Then we are creating simulation to generate the distribution of that statistic under the null hypothesis. And finally, we are saying whether the value that we have calculated on the true data, on the original data, is too high or not. If it is too high, then the place has high risk. Otherwise, it does not have high risk. So that's the crux of the thing. So that's basically the framework. Now I'll talk very light things. For example, the data set that we worked with. we had access to residential records of around 30,000 individuals in the state of New Jersey. And we got it from New Jersey State Cancer Registry. Then to obtain residential records of those individuals, one data linkage procedure has been applied, and one commercial company, LexisNexis, which curate those residential addresses of every person, we linked the data from New Jersey State Cancer Registry to that residential record database. In fact, we did not link it, we don't have authority. New Jersey State Cancer Registry, they linked it, and then we got access to the data. And as a test case, we selected one particular disease, cutaneous T-cell lymphoma, which is called CTCL in short. But there was one problem. So far I have been talking about population, that means people, normal in the sense that they don't have the disease, but how to know the information or the residential records of those people, because they never interacted with healthcare department, and getting access of their residences is not an easy task. So the solution was that we had to use some kind of representative population, not the actual population. So to do that, we found out that colon cancer is a good case, good test case as a control group, because their behavior is more like their actual population behavior. They does not share any risk factor with CTCL. So instead of using actual population, we used colon cancer patients data as a control group for this type of study. Of course, if we know actual population data, it would be even better. But control group, if we use colon cancer patients as control group, that also works well. What we have found out, and the properties of colon cancer is like that. Now I'll talk about some of the challenges. First of all, that residential history data is noisy. It's not easy to collect people's residences, past residential addresses. Sometimes it is incomplete. That means there is gap in the timeline. Often there are multiple addresses listed during a single time period. For example, let's say in 1990, some person has 5 different addresses. So that's a problem. There is overlap in time residential records. And so we had to do a lot of data cleaning. We had to devise algorithms that can clean that data reasonably. There are schemes which are reasonable enough. We had to apply those schemes to first clean the data, then do all these studies in the framework that I talked about. Some details again. For example, matching. I said that corresponding to one case, we have to choose a certain number of controls by matching demographically. But problem is that often, like accessing or getting good matched demographic data is difficult. For example, let's say one case has 40 years old, is let's say female, and his race or ethnicity is this and that. It is very hard to find 5 such people who has got the exact same demographic information as that of our case. So in that case, we have to apply approximate matching, for example, so that we can retain as many people as possible, and also on the other hand, we don't compromise with the quality of our control group. So those kind of details are there, small details. Again, another detail is that in our model, for simplicity, I kept one simple model I showed. But in reality, people like to have some smoothing. What does that mean? Is a neighborhood of a subregion should exhibit similar type of risks. So that's called smoothing, and we had to modify our framework or model to incorporate that effect as well. That changes our loss function, that changes the update rule, but the basic underlying principle remains same. Now the question is, when residential history is useful? As I said, getting access to residential history is not easy, because either we have to do expensive survey or we have to have access to data or the data sources that have those information, and neither of these procedures are straightforward. On the other hand, if we just use people's residence at the time of diagnosis, that data, that information is a lot of times easily available, because when people go to see doctor, they give those kind of personal information. But so why should we bother about using residential history? As I mentioned, because of people's movement. But if people is static, then actually there is no need to consider residential history. The standard method of using people's residences at the time of diagnosis would be sufficient. And now I'll explain some things about the results, findings. We applied this method on the population that I talked about from New Jersey. We found a few high-risk regions corresponding to a particular disease, CTCL. We found that although our study population is relatively static, but there are movements, of course, and that movements changes results if we just consider people's time of people's residences at the time of diagnosis. So in that sense, this type of studies has utilities. We have proved that. One thing is that I have not shared any of the true results because this work has not been published yet, and also the data source is kind of confidential. I'll talk about that next. So we should be aware of these things when we are concerned with personal data or we are doing experiment with human subjects. There are lots of rules, laws, regulations, and ethics related to this type of studies. For example, personally, I had to go through a lot of training to do this type of, before beginning this type of work, I had to go through those trainings so that I get myself familiar with those kind of rules and laws and regulations, what I can do, what I cannot do. For example, I cannot use people's residential address when they are not older than 18 years. Because in that case, if they are minor, then their parents' permission is needed, which often is not taken. So those kind of problems are there. So any study should exclude those information. So we should be aware of those type of regulations, rules. Those are also specific to a very particular country. They vary from country to country. Data privacy is always a concern. If we try to link people's residential address from commercial database to actual patients database in cancer registry, that's a very tricky thing. There should be lots, there in fact are lots of regulations regarding this. We had to have our study proposal approved by some independent committee from other universities. So those type of things people have to, researchers should be aware of, and they should be concerned with. There are some standard approaches. For example, once we have the data, first thing is that we have to de-identify the personal data. If there is, let's say, name or exact address, we have to remove those things so that those things are not accessible to the researcher. Only that de-identified data can be used. Another thing is that people can be identified from their address. So instead of using actual address, we can use aggregated spatial locations. For example, in our case, I told that we have used census tract level data, not the actual address of the people. Because if we have the actual address, then we'll immediately know who has got the disease and who has not. That will be the breach to their privacy. So we should be concerned about those type of ethical aspects corresponding to such studies. So this is, in fact, was a large project. I talked about only the part that I was involved with. I was the person who was working mainly on this framework. But there are lots of other people are involved, a lot of other departments, Department of Geography and Urban Studies at Temple, Department of Computer Science, that is my department. Slobodan is my supervisor, and then New Jersey State Cancer Registry, Trenton, Rutgers Cancer Institute, and Division of Cancer Prevention and Control. So we can see that a lot of departments are involved in this type of studies, and any study we embark on has to go through lots of approvals. And these are essentially the collaborators who had helped to either with the data or with their expertise. For example, CTCL is a special type of disease, and we had to know their exact codes, which patients have got what, because doctors don't write the CTCL, they write their ICD-9, ICD-10 codes, and we had to know those codes. For that, we had some medical expertise as well. So these are the people that I would like to thank. And that is the ending of my talk. End of my talk. I would again like to thank Dr. Adok for arranging this talk. Now I'll take questions or anything that if you want to know in particular. Dr. Adok?
Yeah, that's really wonderful, Aniruddha. Thanks for your nice talk. So I request attendees, if you have any question, please type those. So we will wait for 1-2 minutes for questions, and in future also you can ask some question like from by emailing. You have already.
Yes, of course. That was my mistake to not include my email address in this slide. But please reach out to Dr. Adok for my personal contact information. You are always welcome to contact me in any regard at all, like anything. I am always happy to help.
Okay, yeah. So let's wait for another 1 minute around. So what is the time there, Aniruddha, now?
It's here 8:35.
Oh.
So it was a long talk. Sorry to take all.
Thank you for your nice talk.
It's my pleasure.
Yeah. So I think your talk was very nice. So people they don't have any question really. So we are finishing this session. Okay.
Okay. Thank
and
you.
I personally enjoyed your talk very much. So thank you very much.
Thank you.
Yeah.
Thank you.
Yeah. Bye.
Bye.